We're going to talk a little bit about artificial gravity. For example, this is a real life centrifuge. You might have heard of a centrifuge being involved in something like biology or chemistry when you're trying to separate two different objects based off their densities. You take a cylinder and you spin it really, really fast. You defy the acceleration due to gravity, so you're separating particles is what you're trying to do. But for this one, we're looking into astronauts spending a lengthy time in space. They experience a number of negative effects due to weightlessness. For example, weakening of muscle tissue and loss of calcium in bones. Artificial gravity is created by rotating cylindrical space station can reduce these effects. So for our artificial space station, we can see that the person is inside. The space inside has to be significantly greater than the height of the person in order for the centrifuge to work. What is the speed needed to simulate Earth's gravity? So you're given the radius is 220 meters. This is a top view, so if we're looking straight down on the object holding the people inside. So we would need a free body diagram of the person. The only force acting on the person is the normal force. That is the centripetal force, keeping the person moving in a circle. So we have sum of the forces in the x direction equals F normal, which equals mass times acceleration centripetal. On Earth, F normal is going to equal the weight. So we want to make sure we have the person feeling their own weight, because that's the whole issue, is that they're experiencing weightlessness for too long of a time period, and in turn it's affecting their body negatively. So plug in Fg for Fn, we get m acceleration centripetal. When we're solving for v, or when we're solving for gravity, because we're looking for how are we going to simulate gravity. Gravity is going to equal velocity squared over r. Well, we know gravity, it's 9.8. So if we solve for velocity, that's going to tell us the speed needed to simulate acceleration due to gravity on Earth. So velocity equals the square root of r times g. Plug in our givens, 220 meters times 9.8 meters per second squared. We get 46.4 meters per second. So this particular centrifuge that has a radius of 220 meters has to rotate at 46.4 meters per second. It's pretty fast relative to the size of the radius, in order to simulate acceleration due to gravity of 9.8. So if we're looking for the time for one revolution, well, we just found the velocity in the last problem. It was 46.4 meters per second. We know the distance around one revolution. It's 2 pi r, the circumference. So we can solve for time. Time is equal to d over v, 2 pi r over v. Plug in our givens, 2 pi times the radius of 220 meters, divided by 46.4 meters per second. We get a time of 29.8 seconds. So it's going to take 29.8 seconds for this cylindrical object to rotate, for the object to make one full rotation. How many revolutions per minute is this? Well, if it takes 29.8 seconds to rotate one time, it's going to be about 2. So in 60 seconds, it's going to rotate about twice. But to solve for this, one revolution was 29.8. If we take 60 divided by 29.8, we'll notice that it's 2.01 revolutions per minute.